Welcome to today's paper reading. Today's paper is titled, Jailbreaking Large Language Models with Symbolic Mathematics. This paper, titled Jailbreaking Large Language Models with Symbolic Mathematics, is authored by Emet, Bethany and colleagues from the Secure AI and Autonomy Lab at the University of Texas at San Antonio, Data Science Hub and Core Lab Data Science at Tecnológico de Monterrey, and the Computer Science Department at Florida International University. The paper is currently under review. Recent advancements in AI safety have led to increased efforts in training and red teaming large language models, LLMs, to mitigate unsafe content generation. However, these safety mechanisms may not be comprehensive, leaving potential vulnerabilities unexplored. This paper introduces MathPrompt, a novel jailbreaking technique that exploits LLMs' advanced capabilities in symbolic mathematics to bypass their safety mechanisms. By encoding harmful natural language prompts into mathematical problems, the authors demonstrate a critical vulnerability in current AI safety measures. Their experiments across 13 state-of-the-art LLMs reveal an average attack success rate of 73.6%, highlighting the inability of existing safety training mechanisms to generalize to mathematically encoded inputs. Analysis of embedding vectors shows a substantial semantic shift between original and encoded prompts, helping explain the attack's success. This work emphasizes the importance of a holistic approach to AI safety, calling for expanded red teaming efforts to develop robust safeguards across all potential input types and their associated risks. Large language models, LLMs, are equipped with sophisticated safety mechanisms designed to prevent harmful content generation, aiming to mitigate issues such as misinformation spread, violence promotion, and erosion of trust in AI systems. Recent advancements in AI safety have focused on training LLMs with safety-aligned data and extensive red teaming, primarily involving reinforcement learning from human feedback, RLHF, and systematic vulnerability identification and patching. Despite these efforts, jailbreaking techniques that circumvent AI safety mechanisms remain a significant concern. Our work introduces MathPrompt, a novel approach that exploits LLM's advanced capabilities in symbolic mathematics to potentially circumvent their safety measures. MathPrompt employs a two-step process, transforming harmful natural language prompts into symbolic mathematics problems and presenting these mathematically encoded prompts to a target LLM. Our experiments revealed the alarming effectiveness of MathPrompt, highlighting the severity of the potential vulnerability and the urgent need for more comprehensive safety measures. The methodology involves transforming natural language prompts into symbolic mathematics using set theory, abstract algebra, and symbolic logic. Set theory concepts like is an element of, subset of or equal to, intersection, and union are used to represent relationships and collections. Abstract algebra structures such as groups and rings help model process flows. Symbolic logic, with connectives like and or, and encodes conditional statements. To generate MathPrompt attacks, GPT-4o is employed with few-shot demonstrations, guided by a system prompt instructing it to act as a mathematics expert. This setup allows the model to map natural language instructions to mathematical structures. To engage the target LLM, specific instructions are prepended to each math problem, directing it to solve and provide real-world examples, thereby increasing the likelihood of generating harmful content. Figure 1 illustrates the MathPrompt technique, which exploits state-of-the-art large language models, LLMs, by converting harmful natural language prompts into mathematical problems. This process is facilitated by an LLM, specifically GPT-4o, through few-shot demonstrations. The figure shows how these mathematically encoded prompts are generated and then presented to the target LLM. Additionally, specific instructions are prepended to each mathematics problem, directing the target LLM to solve the problem and provide a real-world example to illustrate its solution. This method increases the likelihood of the LLM generating harmful content, while it believes it is merely providing educational examples. The study employs a dataset of 120 questions about harmful behaviors, with 80% sourced from established open datasets and 20% handwritten by experts. The evaluation spans 13 large language models from OpenAI, Anthropic, Google, and Meta AI, including models with adjustable safety settings. The effectiveness of the jailbreaking technique is assessed using HarmBench, an LLM-based classifier that outperforms GPT-4. The attack success rate, ASR, is calculated as the percentage of harmful outputs generated by the LLMs in response to the prompts. Human evaluation on 100 random samples showed an 87% agreement rate with the classifier, validating its performance. Table 1 presents the attack success rates, ASR, of MathPrompt across various state-of-the-art LLMs. The average ASR is 73.6%, indicating that MathPrompt effectively bypasses safety measures. Safety settings showed minimal impact, with Google's Gemini models only slightly increasing ASR when safety was disabled. There was no clear correlation between model size and resistance to MathPrompt, as evidenced by contrasting patterns across different model families. Figure 2 presents a TSNE visualization of embedding vectors for original, blue, and math, orange, prompts. This visualization clearly shows a distinct separation between the two types of prompts, indicating a significant semantic transformation achieved by MathPrompt. The low cosine similarity of 0.2705 between the embeddings of original and math prompts further supports this observation, suggesting that MathPrompt fundamentally alters the semantic representation of the prompts, allowing them to bypass safety filters while still enabling the LLM to generate relevant responses. The study reveals a significant vulnerability in current safety mechanisms for large language models, LLMs, through the innovative MathPrompt technique. This method achieved an average attack success rate of 73.6% across various state-of-the-art models. The embedding analysis conducted by the authors further highlights the effectiveness of this approach, showing a notable semantic shift that enables harmful content to bypass detection. These findings emphasize the immediate necessity for more robust safety measures that can handle diverse input types, including symbolic mathematics. This calls for increased red teaming efforts and a more comprehensive approach to AI safety that considers all potential vulnerabilities. The study on MathPrompt, while effective, has several limitations. Firstly, the dataset of 120 prompts, although diverse, may not fully represent all potential harmful content. The effectiveness of MathPrompt could differ with various types of harmful prompts or more complex scenarios. Secondly, the study was limited to testing specific large language models, LLMs, and a broader range of open-source LLMs could provide a more comprehensive view of vulnerabilities across different model architectures. Lastly, while the study utilized concepts from set theory, abstract algebra, and symbolic logic, there is room to explore other areas of symbolic mathematics, such as topology or category theory, to enhance the diversity and sophistication of MathPrompt. This work aims to improve AI safety by exposing existing weaknesses and highlighting potential vulnerabilities. However, it also acknowledges the risk that malicious actors could exploit these vulnerabilities to generate and spread harmful content on a large scale. This could lead to issues such as the dissemination of misinformation, hate speech, or even the planning of illegal activities. By bringing these vulnerabilities to light, the research hopes to spur the development of more robust safety measures that can protect against a wider range of attack vectors, including those that leverage mathematical encoding. Thank you for watching.